Welcome to this lecture series in real analysis. We are starting a new module in which we will talk about things like the mean value theorems and whatnot. And for this lecture, let us just recall one thing. We are deep into the course, so we need to know a lot of things, but at least one fact I want to recall, and that is that continuous image of a compact set is also compact, meaning if A is a compact subset of the reals and f is a continuous function from somewhere, let's say some subset S to R, suppose this is a continuous function and A is a subset of S, then f of A is also compact. Okay. Here are some problems for practice. And now let us get started. So we want to talk about local and global extrema. That is the topic of this lecture. So let's at least get a feel for what these concepts are before formally defining them. So I have a function f from an interval. Doesn't have to be an interval, but in this picture, I mean, for the illustration purposes, I'm using a function defined on an interval. So let's say the graph of the function looks like this. And let's talk about the point for which we get this bump. So it's somewhere here. Not the best drawing. I don't want to do it. Anyway, so there is a point here which gives you the peak, so to say. And one can agree that this peak is locally a peak. Meaning what? Meaning if we hover close to the point which achieved the peak, we see, if we just limit our vision to just that much, we see that as an apex. We see that as the top of a mountain. So locally, this is an extremum, rather a maximum, locally. Not globally, because there is another point which gives you even bigger value. So there is a point here which gives you a bigger value. So this is a global maximum, or rather the point which achieves it is a global maximum for the function. But this is a local maximum. Here you have a global minimum. The lowest point the function ever reaches is here. But what about a point like this or like that? They are neither local nor global maximums or minimums, because if you take a point like that, towards the left the function is increasing, towards the right the function is decreasing. So this is neither locally a maximum or a minimum. So these are the basic ideas, and we just want to capture them using formal definitions and see what theorems one can prove about them. So suppose we have a function defined on a subset S of reals. We are not assuming that S is an interval. We have a function and x0 is any point in the set S. We say that f has a local maximum at the point x0 if there is a neighborhood u of x0 such that if you choose a point in u as well as in the domain, what you find is that the value of f at x0 is at least the value you register at the point x. So throughout a neighborhood, x0 remains a peak, or the function f admits or assumes a peak at the point x0 locally. Why we say locally is because we are saying that there is a neighborhood. This neighborhood may be very small, but as long as one exists, we declare x0 as a local maximum. So just correlate with the picture we just saw in the previous page. Okay. Similarly, you can define local minimum. And then there is this common terminology, local extremum. So this is used to denote a local maximum or minimum. All right. Very easy. Now suppose we have a function from again some arbitrary subset of reals, and x naught is any point in the domain. We say f has a global maximum at that point if, you can guess the definition, if right? I hope this is clear why such a definition is there. We saw a picture just previously, and even the terminology itself is suggesting that this should be the definition. The value of the function at x naught beats or is not beaten by any other value that the function takes. Okay, and similarly you can define global minima and global extrema. So minima is a plural for minimum, extrema is a plural for extremum, maxima is a plural for maximum. Okay, very simple definitions. And let's see some examples. So we have this function domain 0, 1 open, and it is the identity function on it. Oops, what did I do? So does this have a maximum, minimum, anything? So here f does not have a local extrema. And if it does not have a local extrema, it cannot possibly have a global extrema, because every global extrema is also a local extrema. Why does it not have a local extremum? Because this is 0, this is 1, the graph of the function looks like that. Clearly no point between, all the points in the domain are strictly between 0 and 1. And no point there is an extremum, because if you go to the left, the function is decreasing, go towards the right, the function is increasing. If this were a closed interval, then clearly we have global extremum, because then 0 would be a global minimum and 1 would be a global maximum. But because this is an open interval, there is no local or global extrema. Okay. Now, suppose we have a function like this. Again, defined on an open interval. So this is the point A and that is the point B. The point A and the point B are not in the domain. They are just suggestively there. Okay, so suppose the graph of the function looks like this. So here, this is a local maximum. This is a local minimum. But there is no global maximum or minimum. Right? Because whatever point you pick, suppose you pick this point, well, if you claim that this is a global maximum, no, it cannot be, because you have a bigger value. If you pick this point, you claim that to be a global maximum, no, there is a bigger value that the function achieves, and so on. So here, local extrema exist, but global extrema does not exist. All right. Now suppose we have the constant function. The constant function 1. Here, every point is, or I should say the function has every point as, a function has a global extrema at every point and a global minima at every point. F has a global extrema, global extremum at every point, and a global global maximum at every point and global minimum at every point. Bizarre, sounds bizarre, but there is nothing bizarre happening. So every point is a local minima, every point is a local maxima, every point is a global minimum, every point is a global maximum. Trivially so. And now here is something that we recalled in the beginning. Suppose we have a compact subset of reals and f is a function which is continuous and has that compact subset as its domain, then f achieves a global maximum and a global minimum, meaning there is a point at which the function has a global maximum and there is a point at which the function has its global minimum. So I'm not writing that, but I've said it. The reason is very simple, as we recalled in the beginning. The continuous image of any compact set is compact. And if you have a compact set, so you just take the image of f. Let's say it is B. Let's say B is the image of f. Now B is a compact set. So the supremum of B is there in B and the infimum of B is also there in B. Take the supremum of B. That is a global maximum for the function, and there is some point in the domain for which you achieve that value. And similarly for the minimum or the infimum of B. Okay. So here is a nice theorem which connects differentiability and the local and differentiability and the notion of extrema. This is something that you may have read about in high school. This is how you optimize things in physics. Usually you want to talk about when the velocity is zero and whatnot. So anyway, what are we trying to say? We are saying we have a function defined on an interval and x0 is some point in the domain. Assume that f has a local minimum at x0. Right? Suppose the function has a local minimum at the point x0. Point number one, if f is right differentiable at the point x0, then the right derivative is non-negative. The right derivative at x0 is non-negative. And a counterpart, if f is left differentiable at x0, then the left derivative is non-positive. So to prove point number one, first of all, when we say f is right differentiable at x0, we already implicitly assume that x0 is not equal to the supremum of I, because then the right derivative of f at x0 would not even be defined. Okay, at any rate, so here is the proof. Since f has a local, so we are proving one. So since f has a local minimum at x0, there is some neighborhood around x0 which has certain properties. So there is some positive delta such that if you choose x in the right deleted delta neighborhood, or just the right delta neighborhood, not the deleted one, right delta neighborhood of x0, we have fx dominates fx0, right? Immediately from the definition of minimum, which implies this thing, and I'll divide it by x minus x0. X minus x0 is a positive number. Because x is here, x minus x0 is a positive number, assuming x is greater than x0. So this is non-negative for all x in this deleted, right deleted delta neighborhood. Right? And now since f is assumed to be right, differentiable at the point x0, we get that the limit, the right limit, it exists. And since we have this inequality for all x in the right deleted delta neighborhood, this will also be non-negative. And that gives us that the right derivative is non-negative. Okay. So that's very nice. And similarly, you can prove the second assertion. We have proven the first one. You can prove the second one. Okay. So here is a corollary. So we have a function defined on an interval and x naught is in I. I really want it to be in the interior of I. Let's see what have I written. Yeah, so I want x naught to be in the interior of I. So what's going on? We have a function defined on an interval, and x naught is a point in the interior of I, so it is not on the boundary of I. And assume f as a local extremum at x naught. Yeah, so whatever we proved in the previous slide, you can prove for maximum also. We proved it for minimum. You can prove it for corresponding statement for local maximum. So here we are saying that suppose f has a local extremum at x naught. And again, remember, x naught is an interior point of I. If f is differentiable at x naught, then the derivative at that is 0. And the reason is very simple. I'm sure you knew this from somewhere before. The reason is very simple. The reason is that since x naught is in the interior and we are assuming differentiability at the point x naught, both the right and the left derivative exist at the point x naught, and they are equal because differentiability means that the right and the left derivative agree. But the right derivative, suppose this extremum is a minimum, so the right derivative satisfies non-negativity, the left derivative satisfies non-positivity, but the equality of the right and the left derivative therefore shows that they both must be equal to 0, and that is equal to the derivative. So that is the proof. Once you prove the previous proposition, this is trivial. But here is one point I want to emphasize, is that just because the derivative becomes 0 at some point, that doesn't mean that you have local extrema at that point. Derivatives are 0 at local extrema, assuming the point at which we are talking is an interior point of the domain of the function. You have a function you have a function defined on an interval. If you pick an interior point and find that the function has a local extremum at that point, and you also find that the function is differentiable at that point, and the derivative is 0. But just because the derivative is 0 doesn't imply that you have a local extrema at that point. For an example, you can, I don't know if I've drawn it here. I haven't. I'll come to that. So let me draw little something. So you can consider the graph of x cube. It looks something like that. Not doing a very good job of drawing it. Just draw the graph of the function x cube. You'll find that its derivative is vanishing at the origin clearly, but there is no local extrema at that point. I mean, this is neither a local maximum nor a local minimum. The function increases if you go to the right, decreases if you go to the left. So fine, this is just a point of caution that I wanted to mention. And now let's just use what we just learned on this simple example. So here what we have is we have a function defined like this. So I'm pretty sure you know how to graph such a thing. The graph of such a thing turns out to be a parabolic shape. It may or may not intersect the x-axis, but typically the shape is a parabola. So suppose we wanted to find where does it achieve its minimum value. And since there is a positive coefficient of x square, you should be somehow familiar that if you go too much to the left side, you will see bigger and bigger values. And if you go too much to the right side, you'll get bigger and bigger values. So it makes intuitive sense, at least, that this function should have a global minimum. And the only candidate for that point, because this is a differentiable function, this is after all a polynomial, so this is a differentiable function. So to locate that point, you find the derivative and equate that to 0. What is the derivative? The derivative is this. And therefore, the only candidate for an extrema is minus b by 2. And if you just play a little bit, you'll be able to show that, yes, indeed, minus b by 2 is a global minimum for this function. So calculus helps to solve optimization problems. And I'm sure you knew this application from before, so I'm not dwelling on it too much. Okay. And yeah, I think that's it, right? Yeah, that's it. So that's all that I wanted to say. As usual, like, comment, share, subscribe. And I will see you next time.